Welcome to the webinar, everyone. Thank you so much for attending. I am your moderator, Joseph Xavier, Director of Marketing, Nuvation Engineering, and we are going to get started. Thank you for attending the webinar, Green Power Grid, Measure, Control, Communicate, presented by Nuvation Engineering and Texas Instruments. Today, we will be discussing the changing architecture of utility grids around the world and what electronic design firms and component manufacturers are doing to address these challenges. We will begin with an overview of the evolution of the smart grid, and then explore the aspect of renewable energy integration, then present an energy storage case study that focuses on grid battery management. You can ask questions during the webinar via your GoToWebinar user interface, and I will collect them and we'll discuss them during a Q&A session for about 15 minutes at the end. For the purpose of maintaining sound integrity, all panelists, all attendees are muted so that we all ensure high quality audio. Our speakers today are Punya Prakash, Business Manager, Texas Instruments.
Hi there. I'm excited to be here today to discuss how we are engineering a smarter grid. I'll be glad to address any questions towards the end of the webinar.
Thank you, Punya. And Stefan Janhunen, System Architect, Nuvation Engineering.
Hello, I'm excited to be here to talk a little bit about battery management systems and how they fit into the grid space.
Texas Instruments is a global semiconductor company operating in 35 countries, serving hundreds to thousands of customers. With 85 years of innovation in embedded processing and analog, we have a broad portfolio of products with an in-depth understanding of industrial environment. In today's webinar, TI will specifically focus on the current challenges in the energy automation and discuss how TI is innovating in this field.
And Nuvation was founded back in 1997 as an engineering design services company. We've completed hundreds of customer projects in really many industries. We started getting involved in the battery management space back in 2009 when we decided to make an electric vehicle as an entry into the automotive XPRIZE. And at the time we had looked at the BMSs available on the market, and we really didn't find one that actually fit our needs, so we decided to go build one. And many years later now, our 4th gen BMS, which we just launched this past year, we've leveraged all of the learning from our own project there and numerous customer projects in this space.
Looking at the evolution of the energy grid, historically the power grid was architected to have a large central power generator sending electricity over the grid to passive customers in home and business. This was predominantly a one-way flow of energy. Not only is this inefficient, but it's also not very economic or environment friendly. The smarter grid of today is on its path to be vastly more decentralized. This, in turn, provides the opportunity to populate power-generating sources, also enabling energy harvesting from renewable sources. Looking at the future of power grid, traditionally the primary goal of yesterday's centralized distribution system was to adequately support and measure consumption, which is unidirectional and a centralized generation, very radial in topology with fewer sensors. A network distribution with heavy sensor integration provides a more granular real-time monitoring ability with the system to remotely test and reconfigure in case of any outages. With the more pervasive control, the overall efficiency of the grid is significantly enhanced. Tomorrow, the grid will require will have the ability to have more control technologies and enhanced data management and communication tools. We're looking at data analytics and cloud integration into the future of the energy grid. Looking at the challenge of the problems that exist in the energy grid, it's mainly challenges in three folds. Firstly, as we look at outage management and recovery, occasional outages do happen due to weather, accidents, and acts of chance. And improved intelligence and real-time information could equip the system to automatically recover and minimize both the scope as well as the duration of the future outages. The second piece is the operations. The goal of power system operation is essentially a stable system. Now, this is especially important as we look at integration of renewables. On a certain day in October 2013, the solar power peaked at 59% of power integration in Germany. And at these, as we look at these unpredictable renewable sources, the stability of the system and integrating it is very critical. The third piece is equipment management. Protection of equipment under fault current surges has always been the primary mission of a reliable network in substation. Going forward, this will expand more into a real-time conditioning monitoring. And this is very critical as we look at continued increase in power demand, which is expected to grow by 84% by 2035. The future of the smart grid is efficiency and reliability of the electricity grid. Looking at the smart grid, a smart grid is so much more than just smart meters. Smart meters represent the customer side of the smart grid revolution. We're looking at increased visibility both into power and information at every single stage in the grid. The webinar today will focus on the role of substation automation in enabling this smarter grid. Substations are the building blocks for a grid. Substation network serves to transform voltage, both stepping up and down, numerous times in multiple locations as needed for safe and economic transportation and delivery of energy to customers. Enablement of smarter grid has significantly changed this transmission and distribution system operation. Looking at Oncor, who is one of the largest transmission and distribution system operator in Texas, historically they used to have a mainframe-based system, and a lot of metering and switching functionality was done manually. This obviously included a lot of labor, not to mention the latency in managing the system itself. These SCADA systems were done by analog phone lines. When you look at their system today, it has transitioned to be more self-healing distribution-based grid. With integration of advanced metering systems, self-healing, just in case there's an outage, it automatically detects an alternative flow of energy, and also with remote sensing integration as well as diagnostic, it's transitioning what the transmission and distribution system looks like today. Now let's go ahead and take a deeper look into what a smart power grid is. The modern substation is foundation for an efficient grid network. We're looking at a lot more data measured. We're looking at data in terms of 5 gigabits per second. So filtering, analysis, and responding to that data presents an ever-increasing challenge. It's becoming increasingly difficult to predict the power needs of the end users. With integration of energy and green power system future, it'll be more difficult to operate and control than the smarter systems of today. We see this challenge of distribution, mainly managing control and communication effectively, as an opportunity. When we look at the application of the substation, the distribution is the very final stage of a delivery of energy to its end users. The intelligent electronic devices in the substation receive the data measured from sensors and power equipment and can issue commands such as tripping circuit breakers if they sense any anomalies in the system. As more and more substations integrate these IEDs for protection and measurement functions, the standard traditional RTUs, which you see in this image here, are becoming more redundant or obsolete. So with increased intelligence in a gateway or a concentrator in substation, the link between IED and control center is all the more important. Enablement of heterogeneous power grid systems, it combines renewables with multiple standby power systems. This creates the requirement and an opportunity for a green optimized grid controller, which can calculate the cost of generating power from all available sources, and this means the renewable as well as the steady energy sources. This can calculate the cost of generating power from all the various sources. Now, with advancements in battery technologies, we would be able to manage and sustain the standby and off-grid power management for responsiveness, regulation, and coverage time. As we look at the technology enabler requirements, the key is integration software, IED, communication and network, sensors, as well as the energy storage system. In the webinar today, first we will discuss the grid management aspect of the substation, specifically the IED functionality and communication enablement. What do we mean by adding smart through the intelligent electronic devices? The communication has transitioned from what used to be traditionally a serial or proprietary bus to a more Ethernet-based communication. This enables real-time communication of the automation functions. It enables operation, monitoring, protection, and overall control of the complete substation. The two key aspects as we look at these IEDs, one is the intelligence, which comes inherently through the networked components with a single core functional doing the monitoring, protection, and control. The second piece is interoperability. As we look at the substation, retrofitting into traditional system is key, which is where the standardization and support for standards such as the IEC 61850 is especially important. As we look at a reliable system, redundancy for an Ethernet-based communication is also key with protocols such as HSR and PRP. As we look at the IEDs, with more sensor integration, we have more data input, which ultimately means an increased measurement. This is also challenging as power equipments are more complex with steady, non-predictable energy sources. This requires for more analytics and control, which gets more complex, with more IEDs in the system of the substation automation. The other piece is communication, support for legacy serial-based or proprietary communication, as well as Ethernet-based platforms. Now, across the platform, as we look at measurement, analytics, communication, what is key is a reliable system. A reliable system hardware, which operates under extreme outdoor conditions, or even as we look at the data reliability with redundancy and enhanced memory correction. Looking at the system in a little bit more detail, the block diagram, with the sensors, there's a lot of analog data coming in through the sensors. So as the first piece, we look at the measurement, we have a lot of ADCs converting this analog data to digital and feeding it into the processor or the brain of the IED. The processor itself, you have the CPU, the memory, the controller unit doing much of the control functions. The analytics, depending on the level of sensor integration, could be handled by a DSP, which performs the analytics. The communication piece is essentially plugged in through the peripherals of the system through Ethernet, serial, parallel, or any such interface. And the system overall reliability spans across measurement, analytics, and control all the way through communication. Texas Instruments has a portfolio of products which enables every single piece as we look at this entire IED system enabling substation. Kind of looking deeper into the controller itself or the microprocessor enabling this, we're looking at a multi-chip, traditionally a multi-chip solution where you had the core, be it an MCU or a microprocessor, doing an HMI or control-based function, and an additional ASIC or an external FPGA managing the analytics, the redundancy, and such functionality. With the TI processor, you would get an integrated ARM processor to manage the control, the DSP to perform the analytics, and optionally, you would enable additional protocol functionality such as industrial Ethernet, Profinet, EtherCAT functionality through the PRU, what's called the PRU, Industrial Communication Subsystem, to offload such functionality so that the control could be purely managed through ARM while you're offloading some of the analytics and communication to cores within the microprocessor. With this, you'll be able to achieve a higher level of overall system savings and have the flexibility to support multi-protocols on a single system. Now, we have traditionally seen that the standards are always changing as we look at these systems supporting PRP or HSR kind of redundancy protocols, not to mention legacy retrofitting with algorithms such as the IEC 61850. With having this flexible core to be able to support this gives the system to be in place for a longer duration, thus looking at lower redesigns as we look at the system solution. The IEC 61850 for synchronization could be enabled on the ARM core, be it a Cortex A8, Cortex A9, or an A15, depending on the level of control that is needed on the application itself. While the redundancy or other Ethernet-based protocols could be offloaded to the PRU real-time industrial communication subsystem, which would manage this outside of the ARM core itself. The benefit we're looking at is a completely programmable and scalable system, which reduces the overall system cost and, more importantly, the complexity of the overall solution. By supporting multiple protocols on the same hardware, it gives the flexibility in the system to be able to adapt to the ever-changing standards, as well as have the scalability as we look at the applications across the breadth of the substation. The next part of the webinar would look more into the renewable energy integration of the substation.
Thanks, Punya. Yeah, so we're going to shift gears and look a little bit at some of the particular challenges we have with renewable energy integration, and then some of the solutions that we've designed for this in the grid space. And fundamentally, the challenge with using renewables on the grid is their inherently unpredictable or variable nature. Simple way to look at this is if you have a solar panel, the sun isn't always shining, so you just can't get power out of it when you want it necessarily. This is a problem for the grid because the grid actually, the AC grid operates at a very tightly controlled frequency. So if you're in North America, you're probably pretty familiar with the 60 hertz AC that's in your wall outlet. And that actually has to stay very close to 60 hertz because the machinery that's connected to it will stop to function if it deviates too far from that, and it can actually lead to outages. And really what that means is the power supplied into the grid actually has to match the load that is being taken out of the grid for that frequency to stay stable. So if you inject power or take out too much at the wrong time, you can get an outage. The solution to this really is a giant buffer in the form of an energy storage system. Now, there are a number of ways of creating an energy storage system, but what we're looking at in particular today is a battery energy storage system. So think of it as just putting a gigantic battery to store your energy, and somehow you want to be able to hook this up to the AC system to help stabilize it and to store the energy for when you need it. So fundamental thing that buffering gives you is it allows you to store energy when it's available, and it allows you to supply it when it's required. And the key thing is that those are often at two very different times when you're talking about a renewable energy source. So looking at the different applications of energy storage, one of the big ones, and it's getting bigger over the next 5 or 10 years, is this renewable energy integration. That's simply because you can store the energy. A second benefit of giant batteries is that they respond very quickly, so we can use them to frequency regulate the grid. And what that means is we can deal with these little fluctuations up and down in the grid by very quickly taking some excess energy off or supplying some required energy exactly when it's required. And that's something that you can do with batteries a lot faster than most other storage technologies, and definitely way faster than traditional generation approaches. So you've got a big battery, you've got a bunch of DC energy that you've harvested and maybe you've stored in there. What do you do with it? Well, without an inverter, you actually can't make that accessible to the grid. The fundamental job of the inverter is to convert DC power to AC power. And in a lot of applications, we use what is actually called a bidirectional inverter, and that actually means that it can go both ways. So you can take power, AC power from the grid, and you can charge your batteries, and you can take DC power from the battery side and you can supply it out to the grid. That's a key property that you need if you want to do something like frequency regulation. And so even if you're doing renewable integration, a lot of times you'll have a bi-directional inverter because it allows you to do both things with the same setup, both get renewable energy and help stabilize the grid. So if we take a step back and just look at the higher level picture of the grid, on the right you can see that variable demand graph that we saw before. And really, if you think about just averaging that out over long periods of time, that's what the steady energy sources, the traditional gas and nuclear, they're good at supplying that. But those peaks and those valleys are really addressed by renewables and battery energy storage. And that's what we're going to look at in a bit more detail next. If you're going to build a giant battery storage system, you've got to choose a battery chemistry. And if you were to go out in the industry today and just look at what's available and what's out there, there's really a whole bunch of different technologies. There's a lot of really cool stuff today that's still in R&D and really might not see mainstream for another 5 or more years. But if we look at what's dominant today, there's 2 really big chemistries. One is lead acid and one is lithium ion. And lead acid does have an advantage in that it is fairly cheap. But some of the new developments in the lithium space are really driving the cost down. So lithium is becoming cheaper. And lead has a really good install base. It's in a lot of applications already. But lithium does have some distinct advantages that are going to further drive its adoption. One of those is the high energy density. So that's just a concise way of saying you can pack a lot of energy into a small space. And if you're trying to store a lot of energy, that's actually quite advantageous because you don't need as much real estate just to set up the storage for that. The other thing that lithium, and in particular some of the newer chemistries are pushing the envelope here within the lithium space, are really high current support. And that's actually important for generating really short bursts of high power. And again, if you're looking at buffering the grid and doing frequency regulation, that's something that matters a whole lot. So that's another advantage to lithium. A challenge with lithium, though, is just how closely it has to be monitored and controlled. And each cell in a typical grid application, you may have thousands of cells to get the capacity you need. Each cell needs to actually be monitored and controlled so that it stays within its voltage specification and its current specification. And if you go outside of those very far or for too long, you'll either damage the cell or perhaps heat up the cell and lead to thermal runaway. You might get a fire starting. So it really requires a battery management system to be connected to this battery and to ensure that everything is operated safely. And looking at a typical BMS, there's really 4 things that it provides. And point 1 we just mentioned, which was safety. This is typically done in multiple levels. So a BMS, first and foremost, you want it to intervene and prevent the system from getting anywhere close to a critical state. And this is typically done by gently ramping things down as it anticipates you might be getting close to some limit. So that's like the gentle control. But then if it's detecting that maybe that's not taking effect or there's been some sudden transient that caused a problem, it will be able to very rapidly just pull all the batteries offline. And that's like your second level that prevents you from going into that critical runaway state. So safety is paramount. Beyond that, the BMS can actually perform balancing. And a simple way to look at that is the goal is to keep all of the cells in your overall big battery pack at a very consistent state of charge. And that enables you to maximize the runtime that you can run off of the batteries, and it also maximizes the lifetime of the batteries. A third thing a BMS provides is monitoring, and this includes statistics and algorithms that are run on all of those cells to see how healthy they are, how they're performing, and just overall statistics of your battery over time. And then all of this information is aggregated and communicated by the BMS out to external systems. And by external systems here, we don't mean websites or interfaces like that, we mean the grid-tied inverter or other systems that are doing data acquisition and things like that. So having set that up, what I'd like to do is we'll look at a case study of Nuvation's BMS, how we've built it, and we'll also look at some of the TI technology that we've used within it to help make this system. When we designed Nuvation BMS, we consciously decided to not put all of it into one box and make it monolithic. We actually designed it as 3 focused modules that can be connected in different configurations to result in a system that really scales to different sizes of batteries. And so we have 3 modules. They're in this picture, the stack controller, the power interface, and the cell interface. And we're going to walk through each one briefly. Starting with the cell interface, this is really the core data acquisition and control module. So it hooks up to each cell in the battery, and it can measure voltage, it can measure temperature, and it can actually perform passive balancing on that battery. So it can take out excess charge when the BMS decides that we need to do a balancing operation. And we have a couple of models of these modules, one that can support 12 cells with just one box, and another one that can support 16. And then what you can do is you can take these and you can connect them up on a daisy chain serial bus, and you can basically build up the system to support hundreds of cells as required. The second module is the power interface, and this does a couple of things. It really sits in the system close to any of the high power, high current stuff, and it does measurements on the overall power and current going in and out of the battery stack, voltage and power and current. And it also controls safety contactors, and it provides the power input for the entire BMS so that we can power the BMS. And we have several models of that as well, because different applications have different voltage ranges, and that means the hardware has to be a little different to support those. Finally, the stack controller is really the central brains of the BMS. And we actually only have one variation of this module currently. And what it does is it connects to the daisy chain of cell interfaces, and it connects to the power interface to create a complete battery management system. And then it owns the overall monitoring and controlling tasks, the safety, and the statistics and the algorithms that the BMS performs. So all of that for a single battery stack is performed within this module. And if we look at how this comes together for a typical grid storage application, it usually looks something like this. So a battery stack is quite simply, you can just think of it as a series connection of hundreds of battery cells. So it can vary widely depending on the application and the battery chemistry, but you might be anywhere from 200 to 400 cells connected in series to get up to your desired battery stack voltage. Then what you need to do is you hook up a bunch of these cell interfaces on the serial daisy chain, and they measure the battery cells and they balance them. And then any of the DC power that goes into or out of the battery stack typically goes through a high voltage section where there's some measurement stuff and some safety control stuff. That's where the power interface lives, and it interfaces to all of that and then communicates back to the stack controller. And then the DC interface of that overall battery stack with all the other components integrated, that's hooked up to your grid-tied inverter. And that is the gateway to take the DC power of the battery and put it on the grid in the form of AC power, or actually use the grid to charge back your battery. If this were a renewable installation, there would be some other ports here that would actually connect out to your solar cells or other things, and then you would have multiple ports where you could charge the batteries. So the stack controller brings all this together because it talks to all of these components. It is hooked up to the cell interfaces for the measurement and control of the cells. It is powered from the power interface, and it allows overall measurement of the battery as a stack at that level. And it also communicates to the inverters and the other pieces of equipment within that local grid site to run the whole system and make sure that it's run in a way that keeps the batteries happy. And that's often done in a lot of applications. We're seeing that as Modbus TCP to the inverter. Now, drilling into the stack controller a bit more specifically, we've actually selected one of TI's processors for use in this module. It's the Tiva TM4C129. And I just wanted to go through a little breakdown of what's running on there and some of our architectural decisions that we did in the software and look at why we chose Tiva. So there's actually a lot going on within a BMS, even though on paper you can describe in 3 or 4 bullet points fundamentally what it does. There's quite a bit that needs to happen to make that happen. And one of the big things that this is doing in the background constantly is data acquisition and control from hundreds of sensors and switches. And that's just something that we run in the background continuously over the SPI bus with DMA. And that's basically a core thing of what the BMS has to do, just because it has to get that data in and it has to control the cells. Beyond that, we do the safety monitoring and control. We run the cell balancing algorithms. There's a bunch of statistics that are computed about the battery stack, and then we have some algorithms that we run for state of charge and state of health. All of these really describe the core BMS functions that are running on Tiva. And to put this into just a little better context, I've shown a bit more of the firmware as a architectural diagram. The blue section is the BMS functions that I just described. That's really only one of 3 really big pieces that have to run on Tiva to make this all work. We actually have a whole portability interface underneath all of this firmware that enables us to run this software on Tiva. And we're making use of a real-time scheduler. We make heavy use of the TivaWare driver library as a building block for our own Nuvation platform drivers. And we've got a full TCP/IP stack in there because we're really seeing when these things are connected together in an overall grid site solution, current installs, like new designs, we're all going to IP-based solutions. So there's a whole bunch of lifting that the Tiva does just to make sure that everything is scheduled on time in a real-time manner and that we have all the protocol stacks and drivers that we need to do what we need to do in this application. And a third thing, which I've shown up on the right, is really just the numerous protocols that a BMS would typically have to talk these days. And beyond just doing the data acquisition and control, we have multiple protocol stacks in there. So we've got Modbus that runs over TCP/IP, but it can also run over RS-485. That's typically used to talk to inverters or other systems. We also have a bunch of CAN registers that can also be used by inverters or other systems, and it really depends on the application, which one you'll choose. And then we have some diagnostic and technician access interfaces that are also still hosted on the Tiva, but it's actually a big chunk of what a BMS does is making that data accessible on different industrial buses to different endpoints so that the whole system can function. Drilling into now some of the things we like in particular about Tiva, we can talk to the high level of hardware integration, and this is one of the reasons why we chose this chip. There's really a lot of on-chip peripherals that map very well to all of the I/O that I showed in the previous diagram. And in particular, the Tiva is a nice part because the Ethernet MAC and PHY are fully integrated into the chip, so we can make a complete low-cost stack controller design that talks IP with very minimal external parts outside of the Tiva. It also supports very large on-chip flash and RAM, and this actually includes an EEPROM, which we find quite handy for storing statistics. This allows us to really store large amounts of code and data, which is what we need for what we do within a BMS. And there's also some features that we're targeting for some potential future applications that would use the hardware accelerated data encryption. So it's nice to have the option of a PIN compatible upgrade down the road for when we need that in our solution. On the software side, we've used TivaWare in the form of Stellarisware some years back and been really happy with how it integrates with our compilers and in our development flow. And TivaWare has continued that tradition. It's really nice working with a driver library that is truly a library that works with many compilers and doesn't suck when you try to put it in an automated build flow. So we have some very particular ways we like to construct software and build it and test it at Nuvation, and the TivaWare library plays well with that. And not only does it play well with that, we're able to leverage the code storage in ROM to actually save some code space. And there's a lot of flash in Tiva, so you might say, how much does that help? Well, in our case, it helps because we end up in situations where we need to support multiple firmware images due to just, we have to have a bulletproof firmware upgrade that falls back to multiple images, and we have a bootloader, and not having to relink in a bunch of driver stuff every time actually does make a noticeable savings on code space, particularly for the bootloader. It's pretty significant. So taking that all together, the high level of hardware integration and just the well-behaved software library, Tiva was really a good fit for Nuvation BMS. We're very happy with our experience integrating it in this product and using it, and it gives us some room to grow as well as we fine-tune and grow the algorithms and the key things that the BMS needs to do over the coming years.
Thank you, Stefan. As the grid gets smarter and more complex, Texas Instruments and Nuvation Engineering continue to innovate to engineer a smarter grid.
Well, thanks a lot, guys. That actually concludes the presentation part of the webinar. It was certainly educational for me, and I hope it was educational for the rest of you. And I really appreciate everyone stayed on during the whole webinar, so I think that we were adding real value. There are a few questions related to mostly to the battery management system, and so I'm going to share them, and we'll have Stefan field some of them. The first question comes from Joe. Are the individual battery cells monitored for end-of-life characteristics? And if so, how is this accomplished? Stefan?
Okay, good question. So I think this is getting at something that would be described as probably a state of health. And so the answer is yes. We do some proprietary things within our BMS to address that. And we actually find that depending on the application, there are really some application-specific things we need to do. So it is something that is tweaked per application and looked at on a case-by-case basis. But at a high level, I can talk to some of the general parameters and how this is done. One thing is looking at just the lifetime of the cells, like how long they've been installed. That's like a calendar type of aging effect. Another one is through looking at the total charge throughput and the cycling of the cells. In other words, how long they've been cycled. An additional way is actually looking at how the capacity changes over time, and this is something that the BMS can actually measure and look at, and it can become a statistic for your battery pack, so you can see that you've actually been losing capacity, and you can see which cell was driving that. And you can also do some things with estimating internal impedance, and as a cell either gets damaged or ages, that impedance will change, and we can look at that and then flag that as an event that may indicate service or replacement is required. So it's a complicated answer, and depending on the chemistry you're using, it's a little bit of a special case. So, and it's something that the industry in general, I think, is actually still figuring out how to do very well. But those are a few ways that you can tackle that, and some of the things that we're using.
Thank you, Stefan. You're going to be fielding a few questions, just to let you know.
Okay.
Herman would like to know, can we use mechanical batteries? And Herman's concern is the lead-acid battery has storage capacity that goes down as a function of time.
Right. So mechanical batteries, I'd have to I'd have to maybe ask a little more about what is meant by that, but there are a number of ways, there are a number of storage technologies that are completely outside of batteries entirely. So, you know, people use flywheels and other things like that. That's not really what we're addressing with this system. But what I will address is, in particular, that comment of the limited cycle life and things aging. And the way that's being addressed within the battery space is actually through new technology. So if you look at something like lead acid, it's a pretty limited lifespan. You know, the cycle count is not that high and it degrades relatively quickly. If you look at lithium, like just a standard lithium, it's going to be potentially factors better than that. If you look at some of the stuff that's coming out in the R&D and the emerging tweaks to the lithium chemistry, in particular research that they're doing with you know, the electrode chemicals and things that's going on in that space. I'm not a chemist, but I've read about it. We're looking at things that can actually extend that out many factors and maybe even up to like an order of magnitude. So you'll end up with a solution that actually can, it's a battery, but it will last 10 times longer than batteries of today or yesterday. So yes, there's other ways to store, but if you want to use a battery, the answer for this field is to actually just drive that research and build better batteries. And we're really on the forefront. We're actually working with a few companies that have some very cool technology that we believe is gonna make an impact in this space. So I hope that answered the question. I took it in a slightly different direction.
Terrific, thank you. We have another one from Vinay, and I'm not sure if that would be you or Punya. I'll read it out, and you guys can decide how to collaborate on that, perhaps. Does the proliferation of inverter-connected renewables give rise to increased fault levels during a fault condition, which then could cause damage to substation protection? Anybody volunteering to field that one?
So I can talk to that a little bit, and maybe Stefan could add to that. The primary goal of the inverters in the solution, mainly for solar management, is for the protection of the unit itself. If I understand the question properly, I guess the question is more related to the fault management of the system itself. Now, as you separate out the sources of energy, the management as it comes into the relay to the back end is more for the IED. And the management of the fault detection and tripping and circuit breakers is managed as we look at the accompanying pieces to the IED, which then plugs into the inverter itself. I don't know, Stefan, if you want to add more to that.
I can add a couple of thoughts. They might not be directly what was asked, but I think they'll shed light on the fault scenario. So one way to look at this is for any complete system, if you were to take a solar farm and put it on the grid, there's multiple levels of fault handling. So at the highest level, there's stuff that's closer to what Punya was talking about, which really makes sure that what the system is doing is not going to be bad for the grid, and we're not going to create some critical faults in the substation. As you keep going down the chain, you'll eventually get down to the BMS, which actually is in charge of making sure the batteries don't end up in a fault condition that could either be dangerous or that would take the whole thing offline. So there's also some stuff that happens in the middle around the inverter just to ensure that that whole subsystem is happy. And a key thing is that there is actually some level of redundancy in most installs. This isn't something we really went into in the presentation just to keep the scope from expanding too big. But you wouldn't typically just have one battery stack. You'd have multiple battery stacks in a grid-tied solution, and potentially multiple inverters, and they'd all be connected together over IP. And that way, if any one subsection of that had a fault, it could go offline, and your capacity would be slightly reduced, but you wouldn't take the whole thing out, and it wouldn't be like this sudden jarring transient event. So it's really, it's by having that some redundancy in your power architecture and having the faults managed at multiple levels that really makes sure that what you're doing to the grid is always very reasonable.
Okay,
So
thank you.
that's what I would add to that.
The next question is from Douglas. Is the battery charging algorithm performed in the stack controller or the power interface?
Okay, yeah, good question. It is performed in the stack controller. So there is a little bit of processing the power interface does, but it's mostly just an acquisition and measurement device. So the place to do the algorithms is within the stack controller because you need visibility into all of the cells that are in that stack.
Wonderful, thank you. And here's a question for Texas Instruments. How many sensors could be integrated into the IED?
The function of the sensor integration, it really depends on the amount of analytics and processing that you would like to perform on the IED itself. Depending on the data that is coming in, the processor that you choose could range, be it a Cortex A8 or all the way up to a Cortex A15. A DSP could be used to upload the analytics that is performed on the sensor itself. If you recall the block diagram that I showed, the amount of sensors that is coming in is gated through the A to D converters that brings in the digital data into the processor itself. So really, the answer is it could depend on the kind of processing capability that exists on the IED and the amount of intelligence you're looking to integrate into the system itself.
Wonderful. Thank you, Punya. And another one, I'm not sure who would field this question, but the question is, which Ethernet protocols are popular in substation automation?
I could take that one to start with. The legacy systems were more serial-based, predominantly RS-485. But if you look at the protocols that are running on top of that in the substation, we've seen Modbus, and I know, Stefan, you mentioned a couple as we look at the battery management system specifically, and you mentioned CAN as well as some of the interfaces. Now, newer, latest technology, we're looking at Ethernet-based protocols, and the influence, it depends on the kind of sponsor that exists for enablement of this industrial Ethernet. Where we have seen traditional TCP/IP kind of Ethernet protocols, there's more influence from sponsors such as Siemens, which enables Profinet technology, or Ethernet IP from ODVA, or EtherCAT from Beckhoff and ECG Group. So the range of industrial Ethernet protocols is quite vast and diverse, but it is dominated based on the adaptation from these key sponsors. The flexibility that the Texas Instruments processor brings in is with the programmable real-time industrial communication subsystem, which gives the leverage to be able to adapt any of the trending industrial Ethernet protocols, as well as to adapt to some of the changing technologies into the processor.
Thank you, Punya.
I can add
go ahead.
something really quickly. Sorry, Joseph. I agree with the Modbus. There's kind of two answers to that. There's a legacy answer, which is the RS-485 base, which for many legacy systems is actually pretty popular. That's something that's still out there in an installed base. But pretty much anything new that's going in, if you're trying to communicate with the BMS over Ethernet, a lot of people are using Modbus TCP, and there's actually an open standard out there right now. It came out of the solar inverter spec, but it's called MESA, M-E-S-A, and it's something that Nuvation is helping to contribute to. But we're trying to create some nice plug-and-play interfaces using Modbus TCP for what a battery management system looks like. So in our space, we see a lot of the Modbus. We use CAN. We do some custom things over other protocols, depending on the application, but definitely Ethernet is the way to go.
Thank you. We do have somebody who would like to know your secret sauce, Stefan. What is your cell balancing method and capability?
Okay, secret sauce. Well, this isn't too secret. We do have a proprietary algorithm that we use, but at a high level, what our balancing does in our current cell interfaces that I was showing, it's passive balancing. We just find that that's very cost-effective for a lot of applications. We're certainly aware of active balancing, something that's on our radar, but it's for most applications, it's not cost-effective. And so our off-the-shelf hardware, typically we can balance things passively with 200 to 300 milliamps of balancing current, and that works for a lot of applications. For applications where it's not enough, we just customize the cell interface, and we can do whatever is required there. So hopefully that answers the question.
Great, thank you. We might have a technical problem. I'm getting a strange readout on my computer saying connection lost. I will pass control over to somebody else just in case. Now, while we do that, I'll ask another question. And the question is, our chemistry is a bit unique in certain situations, can go all the way down to 0 volts per cell. Can your BMS still operate with no cell voltage?
So I guess that's one for me. Yes, absolutely. So we designed it, a detail I didn't get into was in the actual link bus, we actually run power down that bus to the cell interfaces. So we're actually seeing, we're familiar with a chemistry as well that can go right down to 0. So with our BMS, you could completely discharge the battery right down to 0 volts and charge it up, and everything would still work. So that was definitely something one of our previous generations didn't do, and when we set out to design this one, we said, yeah, we need to do this. It also opens up using things like super caps or other things like that for alternative storage approaches that look sort of like batteries. So definitely we can do that.
Wonderful. So we've got time for one more question, and it's a question that comes up in just about all new technologies that are applied to distributed systems, and that is, what level of security is typically required in these systems, and how is that typically handled or provided? And maybe I have a feeling that both Punya and Stefan, you'd probably have maybe different perspectives on this from your various vantage points.
Sure. The level of security on the grid depends on which segment of the grid that we are looking at. As we look at the end nodes where you have the consumers with the meters being deployed, you have a certain level of security. And as you backtrack towards the grid side of things, the generation, the level of security is of course different. At the end nodes, we're looking at a heavier security because there's a lot of data involved, data analytics, data control, which could be used for benefit, of course, but there's also a disadvantage that it inherently brings should it be hacked in some way. So as we look at the system security, what is predominantly used is cryptography, as we look at encryption of the data itself, where the key for protecting the data is held only by the key utility providers or the end customers based on how they set up the system. That ensures the protection of the data as they're looking at transmission from the end nodes to the mid-end to the back end. As we look at the systems for distribution, systems in the utility, providing the service itself, the processor that is deployed in these units, they collect the data. So the data storage of this, again, on the system encryption, but again, the key is stored in a secure memory within the processor. So even if anybody did get access to it, unless you have the key, you would not be able to decrypt the message to be able to gain access to the details of the stored data. And as we look at the device itself, again, there is something called tampering, where the device could be tampered potentially to retrieve this level of data key. Now, if the key is lost, obviously you'll be able to infer the stored data by using that. One way to protect this is to have an increased security in the system to provide what's called a tamper protection. There are different levels of doing this, the highest level, which is typically used in, say, a point-of-sale unit where you're doing transactions, is used where it's monitoring every single change in the peripheral, be it the voltage, the signals that is coming in and leaving from the system. As soon as any anomaly is detected, it completely shuts down the system, so nobody would be able to access that level of data. So again, grid is so broad. We're looking at end-to-end system from distribution to the end nodes. So depending on where you're looking at, the level of security is different. The packets could be encrypted, the device could be secured with different keys, and the device itself could be secured with a higher level of tamper protection.
Okay, thank you very much, Punya. That concludes our webinar. If you would like to check out Nuvation's battery management system, you can just go to our website and click on the BMS link, and you can go to our contact page and send us an email via that, and someone will get back to you quickly. Punya, if there are any of the processors or if somebody has some questions about your components, thinking of integrating them into their solutions after this webinar, how would they reach out to Texas Instruments?
Feel free to visit the ti.com applications page. We have a lot of details on the various smart grid applications, inclusive of the substation automation as well as the intelligence electronic devices. In addition to that, you can feel free to look at the E2E support forum. We have a huge database of questions that we have addressed specifically in addition in lieu of these processors.
Wonderful, thank you. And for those of you who would like to check out this webinar again in the future, or well, I guess I can't talk to the people who've already dropped off because they're not here, but we did record this webinar, and I'll send an email to everyone who attended to let you know when the recording is available, so you can check that out at your leisure. Thanks so much for hanging on and listening to what we had to say about the smart grid. I hope it was interesting and valuable to you, and I look forward to sharing another webinar with you in the future. Take care, everybody. That concludes our webinar.
Thank you.
Thank you.